I would like to look at a physics problem in two different ways, as a Physics 1 problem and as a Engineering 101 problem. So if you have a beam sticking out from a wall and supported by a cable, then you have an unknown force X and force Y acting at the point of connection. And the rope is necessary to keep the thing from falling over, to supply the torque required. So we can use torque as RF sine theta, sum of forces X, sum of forces Y, sum of torques, all of those equal 0. And we find out Fx is this, Fy is half the weight, and the tension is mg over 2 sine theta, so more than half the weight. Now let's remove the rope. Right? If there's no rope there, then what's going to keep the beam from falling down? Well, if you literally in real life, like take a board and stick it to a wall, if you attach it firmly enough, it will stay put. So how is it doing that? The connection, the place where it's hooked on, is the only place there's going to be any force besides gravity. That is going to have what we call a moment. Basically, we call it torque in physics, and we call it a couple or a moment in statics. So how does this work? Well, the diagram is a little simpler. Instead of having that tension, we've got that. So the equations come out much simpler as well. We don't need any force in the x direction because there's no rope pulling left. In the y direction, it has to hold up all the weight. And then there's a moment, a twist being applied at the end, which is mgl over 2. So that's an engineering way to deal with a board that's just sticking out, which in a Physics 1 problem, we wouldn't write that because we haven't been talking about that in that detail. Here's another complication we can add. In addition to having this force X, force Y, and moment, instead of having mg, I'm going to have a distributed weight. It's mg over L is sort of the density of the weight. If you work out all the details in this example, you get the exact same answers as from this, in terms of what they call reaction forces, force X, force Y, and the moment. But distributing the load is more like real life, right? Because you don't actually have all of the weight perfectly there in the center. Some of the weight is here, some of it's here, some of it's here, all the way along. In a problem this simple, it doesn't make a difference. But you can do more elaborate problems where you start to worry about, well, how much stress is it under this far down? And so these are the first steps along the way of going from physics to engineering statics. When I work engineering statics problems, it feels like I'm working tricky Physics 1 problems, except, with an accent. The details, the labels are a little funny looking to me because I naturally am thinking in terms of Physics 1. But it's the same material, just done in much more elaboration and depth, and they can do many more things in engineering statics, go into more detail, more realism, because that's what you need when you're going to build a bridge.